about that spatially in terms of what the water table means. The water table is the point at which the water level would come to in a macro pore, which is effectively a dip well. So if you sink a dip well into the soil, this is what you'll measure. But as Lawrence was showing us in his diagrams, above the water table you get something called the capillary fringe, where all the other pores, other than macropores, are still water filled. So the soil is still functionally saturated for a distance that might be 5, 10, 20 centimetres above the water table. And then above the capillary fringe you get into the unsaturated zone, where you still have water, and the water, I mean, this is just a slice through it, but those blue bits may well connect up by quite tortuous routes, so that if water's evaporating from the top, it may be resupplied via this three-dimensional network of small pores by a process of capillary rise. So the unsaturated zone, the moisture tension within it is still controlled by the water table depth. So we've always argued that water table depth is the best thing to measure, because although it's strictly only telling you where the saturated zone starts, if you understand your pore size distribution of the soil above the water table, then you can fairly accurately predict what the tension, the availability of water in the rest of the profile from the water table position. So in wet soils that we generally deal in, the water table is pretty well describes what you need to know for water availability, but as Lawrence pointed out, especially in sands and very coarse soils, water table will drop to a point where it gets disconnected from the surface and the root zone, and then it doesn't matter where the water table is. Once you've lost that hydraulic connection via these small pores, the plants are blissfully unaware of where the water table is. Okay. So I won't go on any more with that presentation.